Okay, I wanted to talk a little bit about the absolute value function and ways to work with it in practice. So think about the definition that you have for the absolute value function. One of the first definitions that we are given for the absolute value functions is just the distance of the number from 0. So the absolute value of x is the distance from x to 0. This means that if the absolute value of the number 3 would be 3 because the number 3 is 3 units from 0. And likewise, the absolute value of the number -3 is also 3 because the number -3 is 3 units from 0. Okay. So another definition that you might remember is that the absolute value can be defined in this piecewise manner. That the absolute value of x is x if x is positive, and the absolute value of x is the opposite of x if x is negative. And thinking about what this means if x is positive, then it's just x because it's that distance from 0 in the positive direction. If x is negative, it has a negative sign in front of it, so the opposite of x would be the positive of the same size, right? The positive number of the same size as x. So another way that sometimes people refer to the absolute value is you just take the number and kind of chop the sign off of it. If it has a negative sign on it, you just lob that off. And in some ways, this piecewise function kind of does that. That the absolute value of some number is just like take that number, but like take the negative sign off if it's there. And that is basically saying that like if the number is negative, then you take the opposite of that number, which is just taking the negative sign off of it. Okay, another definition of the absolute value that some people are less familiar with is this one, which is the square root of x squared. Now, some people think that the square root of x squared is x, but if you think about this, if you put in, for example, -3 for x, then if you take the square root of -3 squared, that's the square root of +9, and the square root is defined to always be have a positive result. So this is +3. So I put in a -3 and I got a +3 out. So if you kind of think about what's happening in this function, it is doing the same thing as the absolute value function. Now, this might be a strange way of representing the absolute value function, but it actually is very, very consistent with thinking about this notion of the distance of x from 0. And I want to bring in a couple of other examples here just to kind of make this a little bit more clear. If you are in a two-dimensional situation where you have a point x comma y, some coordinates of a point, if you want to look at the distance to the origin, then you would use the Pythagorean theorem and say the distance is the square root of x squared plus y squared. Okay, I mean, you might start with saying d squared is equal to x squared plus y squared, but then solving for d, you get d is the square root of x squared plus y squared. And if you look at a 3D kind of model, then what you have is a point in space is defined by 3 coordinates, x, y, and z. And so, like, you can kind of see that the dimension in the 2D space, that is going to be d, where d is the square root of x squared plus y squared. And then the distance from the origin to the point x, y, z, let me give it a different color. So this distance here, I'll call it a capital D. Well, I can see that capital D squared, capital D is the hypotenuse of a right triangle, kind of sitting on that diagonal. And so capital D squared is little d squared plus z squared. If you can see that, take a moment to see if you can see that triangle. And so that tells you that capital D squared is, well, little d squared is x squared plus y squared. And then we have plus z squared. So capital D would be the square root of x squared plus y squared plus z squared. So if you look at 2 dimensions and 3 dimensions, there is this consistency of the format of the formula for the distance from a point to the origin. And breaking that down to 1 dimension, you can see that the distance from the point to the origin, regardless of the number of dimensions that you have, is the square root of the sum of the squares of all the dimensions. Okay, so in 1 dimension, it would be the square root of just the one number squared, the one coordinate squared. Okay, so this is one way to kind of tie all of these in. And there are kind of different reasons to use each of these different depictions of the absolute value function. But a lot of times when you're working algebraically with the absolute value function, a lot of times it works to kind of focus on that piecewise definition. So we're going to do that for a few different examples. First example here, we are going to look at the absolute value of x plus 3. So that absolute value function, if I think about that in piecewise terms, this is going to give you, the output is going to be x plus 3 if that x plus 3 value is a positive number, and it's going to be the opposite of x plus 3 if that x plus 3 value is a negative number. So let me write that. It is going to be x plus 3 if x plus 3 is positive or equal to 0. If it's equal to 0, then both of these formulas will work. And it's the opposite of x plus 3 if x plus 3 is a negative number. So I'm going to rewrite this a little bit. This is x plus 3 if x plus 3 is positive, that means x is greater than or equal to negative 3. And this would be negative x minus 3 if x is, and I wrote that incorrectly here, x plus 3 is less than 0. So if x is less than negative 3. Now if I wanted to graph this, here is at x equals negative 3. If x is greater than or equal to negative 3, so on the right side of negative 3, this is the line x plus 3. So that's a slope 1 and y-intercept of 1. So that looks like this. Sorry, slope 1 and y-intercept of 3. And if x is less than 3, it's going to have a slope of negative 1 and y-intercept of negative 3. So I look at negative 3, but I'm not graphing it over here because those represent x values that are greater than 3. So I want the ones that are less than 3. Continuing that line, it's going to go like this. Okay. And I'm just going to erase those little pieces. That was helping me to get that line, but it's not part of this graph. Now, you might recognize this as a transformation of the graph of y equals absolute value of x translated to the left by 3 units, which fits with the transformation of functions. But I think it is useful to see this as really just straightforwardly using the definition of the absolute value in the piecewise definition. Okay? So let's look at this piece. Again, you can look at graphing this function by using a transformation of the absolute value function, but let's look at it by the definition of absolute value as the piecewise definition. So in the piecewise definition, that absolute value, the breaking point, the point where it shifts its definition is where the absolute value piece is positive or negative. And so the point where that breaks is where the absolute value piece hits 0. So we're going to have one formula for if the piece inside the absolute value, which is x, is greater than or equal to 0. And then there's another piece for if the thing inside that absolute value, x, is less than 0. So if x is positive, then the absolute value of x is x. So this is going to be 3 times x minus 5. And if x is negative, this is going to be 3 times the opposite of x minus 5. So let's rewrite this. It's going to be 3x minus 5 if x is greater than or equal to 0, and negative 3x minus 5 if x is less than 0. So I'm going to give some room down negative 5. Here's x and y. We should put those here. So if x is positive, then 3x minus 5, so y-intercept of negative 5 and slope of 3. So it's going to start here and have a slope of 3. I'm actually going to use my straight edge tool here. Like that. Okay. And if x is negative, we're going to have the same y-intercept and slope of negative 3. So I'm going to go like this. Again, we could use transformation of functions to say this is taking the absolute value function and scaling it vertically by a factor of 3, and then shifting it down by 5 units. But we're evaluating this just by straight piecewise definition of the absolute value function. All right, let's look at this one, because this one cannot be done with a transformation of functions. All right, so let's look at this. So this is going to be it's going to break wherever this function becomes positive or negative. So we're going to have one thing if x squared minus 1 is greater than or equal to 0, and another thing if x squared minus 1 is less than 0. Now, if the thing inside the absolute value is positive, then the absolute value is that thing, x squared minus 1. If the thing inside the absolute value is negative, it's going to be the opposite of that, negative x squared minus 1 in parentheses. All right. Now, it is worth kind of dissecting what causes x squared minus 1 to be positive or negative. So x squared minus 1, there's all different ways you can break this down. X squared minus 1 is the same as x plus 1 times x minus 1. And so something you could do, you could break this down and say there are two breaking points for this thing. X squared minus 1 is equal to 0 at x equals plus or minus 1, right? This gives us a 0 at x equals negative 1, and this gives us a 0 at x equals positive 1. So we could do that and say, okay, we could break down for x less than negative 1, for x between negative 1 and 1, and for x greater than 1. And we could break down the factors. There's x plus 1 and x minus 1. X plus 1 is negative to the left of negative 1 and positive to the right of negative 1. X minus 1 is negative to the left of positive 1 and positive to the right of 1. So multiplying these, so x squared minus 1 is the product of those two. So for x less than negative 1, negative times negative is positive. For x between negative 1 and 1, positive times negative is negative. And for x greater than 1, positive times positive is positive. That is one way to see it. Another way to see it is x squared minus 1 is the transformation of x squared down 1 unit. So it looks like this. And it has intercepts at negative 1 and 1. And so we see the y coordinates are positive to the left of negative 1 and to the right of 1, and negative to in between those two x coordinates. Okay. Now, this means that we have analyzed this breaking point. So absolute value of x squared minus 1 is equal to, well, if x is less than negative 1 or greater than positive 1, then we're in this situation where x squared minus 1 is positive, so the output is x squared minus 1. If x is less than or equal to negative 1, or x is greater than or equal to positive 1. And then the point where x squared minus 1 is less than 0 is the same as x is between negative 1 and 1. That's where we have negative x squared plus 1. Now, if we graph those pieces, x squared minus 1 x squared minus 1 looks like this. I'm going to take that x squared function okay, This is y equals x squared minus 1. And so we would graph that function only on the outsides of -1 and 1. So I'm actually going to remove this bottom piece. Okay. Now, if x is between those, I would do -x squared plus 1. And that is -x squared kind of looks like this. And if I move it up 1, then I'm going to have this piece here. All right, and if you think about why this would happen, another way to reason this is here is the graph of y equals x squared minus 1. And basically what we're doing is we're going to take all of those negative y values and flip them up and take their opposites. So we would take all of the parts of the graph that are below the x-axis and flip those up and reflect them up into the top half. Okay, but this is, again, this is using the piecewise definition. All right, now let's look at something like this. So this has two different parts of absolute value. And those two different absolute value pieces are going to have different breaking points for the piecewise definitions of them. So this one is going to be x if x is greater than or equal to 0, and the opposite of x if x is negative. And this one here, absolute value of x minus 2, it's going to be x minus 2 if that stuff in the absolute value, x minus 2, is greater than or equal to 0. And it's going to be the opposite of x minus 2 if x minus 2 is negative. All right, I'm going to rephrase that x minus 2 piece a little bit and say it is going to be x minus 2 if x is greater than or equal to 2, and it is going to be negative x plus 2 if x is less than 2. Now looking at these pieces, we have kind of 4 different possible combinations depending on whether x is greater than or less than 0, and depending on whether x is greater than or less than 2. Okay? And so I say 4 different choices, but there's one choice that's not an option. It's not possible for x to be both greater than 2 and less than 0. Okay, so basically we have 0 and 2 as breaking points. And so this function, absolute value of x, plus the absolute value of x minus 2 is going to be equal to there's going to be 3 different options here. One if x is less than 0, one if x is less than or equal to, greater than or equal to 0 and less than 2, and the other one is going to be if x is greater than or equal to 2. Okay, so if x is less than 0, so let me actually put in color code this. If x is less than 0, then that means I'm in the less than 0 portion of the absolute value of x, and I'm also in the less than 2 portion of the absolute value of x minus 2. So in this case, it is negative x, the absolute value of x is negative x, and the absolute value of x minus 2 is negative x plus 2. Okay, let me find, how about green for the next one? If x is greater than or equal to 0 and less than 2, then that means absolute value of x, we are in the greater than or equal to 0 portion, and less than 2, we are in the less than 2 portion. So the absolute value of x is x, and the absolute value of x minus 2 in this case is negative x plus 2. And now if we have x is greater than or equal to 2, let's see, what color can I use? Let's use red. In this case, we are going to be, if x is greater than 2, then x is greater than 0. And if x is greater than 2, then x is greater than 2. So we're going to be in the positive portion of both of those. So absolute value of x is x, and the absolute value of x minus 2 is x minus 2. All right, so let's clean this up. Absolute value of x plus the absolute value of x minus 2 is equal to, in the x less than 0 portion, this is negative 2x plus 2. That's how that simplifies. If x is between 0 and 2, this looks like x plus negative x is 0, so that is just 2. And if x is greater than or equal to 2, this is 2x minus 2. And so if we graph this, this should be all positive numbers. So if x is less than 0, it's negative 2x plus 2. So it's like this. Okay. If x is between 0 and 2, then the function is just the constant 2. And if x is greater than or equal to 2, the function is 2x minus 2. So at x equals 2, that value is 4, and then the slope is 2. So it would be like this. Joop, joop, joop. Okay. So you might, if you were to encounter the graph of this first and try to figure out how to write a formula for this graph, you would probably come up with this piecewise function, but it turns out you can also write a formula for that graph using the absolute value of x plus the absolute value of x minus 2. I can tell you, I do not have the skills to figure out right now how I would start with the graph and come up with that sum of absolute value functions, but that could be a fun challenge. Regardless, this is a couple of examples of actually working with the absolute value function as a piecewise function to see why it is producing the graph that it is producing.